this reoriented approach does not explicitly form a prior model over shapes. So we directly map from an image to a 3D shape. Those previous methods are also rely on strong supervision, full supervision, in the form of a data set of images paired with 3D shapes. So that annotation is very expensive to obtain because we have to build the data set of 3D shapes, and also we have to pair each 3D shape precisely with an image. And that motivates us in this work to consider the case where we only have 2D images to train from. We don't have any supervision. So our overall approach here is going to be to build a generative model of 3D shapes, but using only 2D images to train that model, so without any annotations, without any 3D data. And to do that, we'll jointly model shape and pixels, and reconstruction will then be cast as inference of the most likely shape, given the observed pixels. To make this tractable, we make the assumption that our images are like the ones on the slide, so they contain just one object of a known class on a plain black background. That's similar to the handful of prior works that also consider this 2D supervised setting for 3D reconstruction. And those works, which are at the bottom of the slide there, all require some form of 2D supervision, which ours doesn't. So they either need pose annotations on every image, or key point annotations, and some of them also require multiple views of each instance to be presented together at training time, whereas our method doesn't require any of those things. So, how do we do this? Well, our approach is inspired by the variational autoencoder, or VAE. The VAE is a deep generative model of pixels, images, and to sample an image from it, we first draw a sample from a latent Gaussian distribution Z, then transform that sample with a neural network to give pixels. Finally, we add Gaussian noise to those pixels to give the final image. To train that model, ideally we would use maximum likelihood. We'd maximize the likelihood of a training set. But that's intractable because we need to integrate over that latent variable Z. So instead, we introduce an encoder network, which is another neural network that's trained to predict the latent code Z for a given image X. That encoder can be used to define an approximate posterior distribution on Z. And then, instead of maximizing the training set likelihood, we maximize a lower bound in it called the elbow, which is effectively given by replacing the posterior distribution with the approximate posterior defined by the encoder network. That objective can be split into two parts. The first encourages the model to correctly reconstruct pixels via its latent space in the two neural networks, and the second term encourages it to match the prior distribution, so the approximate posterior matches the prior. Now, that's a nice generative model over pixels, but we want to deal with the 3D case. So what we do in this work is we augment the decoder with an explicit representation of 3D shape. So we still sample from a Gaussian distribution, a latent code, and pass that through a neural network. But now that neural network produces a 3D shape instead of an image directly. And that 3D shape is then rendered to give the final image pixels, still within the generative model, and then, again, Gaussian noise is added. So this is still a deep generative model of pixels, but it's now one that explicitly reasons over 3D shapes. And because it's still a model of pixels, it can be trained end-to-end, just using images as the training data. And again, to make that training tractable, we have an encoder network that predicts the latent embedding for a given input image. So, we know that in practice, the same object can actually appear at different poses, as well as having different shapes. And so we also add a second latent variable, theta. In this work, that's just the azimuth angle. So that's sampled separately from the shape and is passed into the renderer to define how the shape is rendered in image space. And again, we add another output to the encoder network so that it predicts theta as well as Z. So as well as doing single image reconstruction via the encoder and decoder, we now also perform pose estimation when the encoder predicts theta, and both of those tasks without any explicit supervision. They're learned just from 2D images. And ideally, we would just train that as it is for the elbow, but in practice, this collapses to a solution where it doesn't make use of the pose variable. The pose always predicts a single value, and the shape accounts for all the variability in images. And to mitigate that, we bin the pose into coarse settings and then add a Gaussian offset to each. And then that means we can integrate over the coarse poses. And that's enough to encourage the model to use the pose variable as well as the shape to account for images. I said we produce a shape representation from the neural network. Prior works on 3D reconstruction with 2D supervision use voxels as that representation. But voxels don't produce very pretty images. They're blocky. And also they're expensive to produce from 3D CNNs, require a lot of memory, a lot of compute. Instead, we use 3D meshes, which are a more lightweight representation. Obviously, they're very widely used in computer graphics. And we use 3 different parameterizations that are used to build meshes from our neural network. The first parameterization is based on cuboidal primitives. So for a fixed set of cuboids, we predict a translation and a scale. The second parameterization, again, is based on cuboidal primitives, but now we also predict a rotation for each as well. And the final parameterization is based on freeform deformation of a unit cube. So we start with a unit cube, we subdivide it, and then add an offset to each vertex, with those offsets being predicted by the decoder network. Okay, moving on to our experiments. We use the ShapeNet dataset as a source of data, but we render images from that, but we discard the 3D shapes after rendering the images to produce training data. So we don't train using the 3D shapes, we just keep them to evaluate on. And we use 4 classes from ShapeNet: car, aeroplane, chair, and sofa. And this shows examples of meshes sampled from our model for each of those classes. So these aren't reconstructions now, they're just samples drawn from the learnt prior model by drawing a Gaussian Z. And we see that in each case, the model produces quite realistic samples for each class, and also they're diverse. So for example, for sofa, we have both straight and right-angled sofas. For aeroplane, we have both delta wing and straight-winged. And yeah, we can also look at reconstructions then. So the previous slide was generations where we didn't have an image. In this case, the left-hand column is an input image now. The center column in each group is the reconstructed model orientated at the predicted pose, and the right-hand column is the same reconstructed model, but rotated to a canonical orientation so we can see it. And we see that the center column generally matches the left rather closely, so we're successfully reconstructing the input pixels, and also when we rotate that shape to face the camera, we see that the reconstruction is also realistic. The model has filled in the hidden regions well. Moving on to quantitative results, here we evaluate the mean intersection over union of our predicted shape with the ground truth. And we see, so the columns here represent the different parameterizations I described, so primitives for rotation, and deformation. And we see that different parameterizations work better for different classes. So the primitive-based parameterizations work well for object classes that are physically built out of compact parts, like aeroplanes and chairs, whereas deformation works well for cars, which are smooth surfaces. We can also evaluate performance with pose supervision given. So I said we're fully unsupervised, we don't require pose, but you can also feed it into the model at training time, so it doesn't have to learn to disentangle shape and pose. And that makes the task easier for the model, and we see that in the right-hand column the numbers are consistently higher, so the model can exploit that extra supervision. We also looked at the case where we don't have shady information. So I said a benefit of using meshes is that they can represent arbitrarily oriented surfaces. And that means that if the model reconstructs a surface at the wrong angle, it gets a feedback signal encouraging it to correct that because the shading is wrong in the reconstructed image. To test whether that's truly beneficial, we also ran experiments where we didn't use shading in the reconstruction loss, we just used the silhouette. And we see that that's consistently much worse than in the case where we have shading, the left-hand column. As a special case of that, we also looked at using different lighting on the model, so both coloured 3-directional lighting, which intuitively provides a lot of information about surface normals, and unidirectional white lighting. And again, we see that the model is able to exploit that extra shady information that we get from tridirectional light. Finally, we also compared our method to some state-of-the-art 2D supervised methods. So these methods train from 2D images, but they require stronger supervision than us. They need pose annotations and to be given multiple views of each instance. And we see that our method, in spite of not requiring that extra supervision, performs better on them for every class. We also compared with a 3D supervised method. So this has access to the full ground truth 3D point clouds. And that performs slightly better than ours, but it's still only a little better. And for one class, it's almost the same. So even though our method has only 2D supervision, it performs nearly as well as the 3D supervised method. Finally, we can also evaluate the performance on pose estimation by the encoder network, and we see that the median predicted error in poses is rather small, and also we're typically within 30 degrees of the correct answer. So the model is successfully disentangling these shape and pose factors. And that's all. So to conclude, I've shown that it's possible to learn 3D reconstruction just from 2D images. And to do that, we presented a generative model over 3D shapes, which you can also sample shapes from a priori. And that model learns to disentangle shape and pose. Thank you.
Are there any questions?
Yes, that's correct. In the experiments we used 6 cuboids in some case and 12 in the others. So yes, it's always fixed. And similarly for the subdivided cube, we fix the number of vertices. We don't try to vary the mesh topology. Yes, this is an interesting question. So we already have one rotation angle in there, the azimuth. It would, in principle, be straightforward to add another rotation angle, and also, as you suggest, also the lighting parameters and so on. We haven't tried that, no, but it's an interesting direction for future work. It becomes much harder for the model because now it has to disentangle a lot more factors. And in particular, we currently, as I said, have to integrate over the space of poses. And if you have 3-dimensional pose and 10 directions of lighting, and you still need to integrate, then that will become computationally heavy. But in principle, yes, it should work, and it would be interesting to try that. Okay? Thank you.
Good morning, everyone. I'm Ming from University of Adelaide, Australia. This work I will talk about is about real-time molecular object instant 6D pose estimation. This work is under collaboration with Tuan Du, who is a postdoc in our group, and Chuan Pan, who recently started his career in NVIDIA. This work is also supported by Australian Research Council through Australian Center for Robotic Vision. Please allow me to start with the problem we're trying to solve in this work. Yeah, okay, good. The objective we want to try solving our paper is object 6 degree of freedom object pose estimation. As we all know, pose estimation is one of the fundamental problems in computer vision. It tries to find the geometry relationship between the camera and the reference system. The reference varies from each other. It could be the world coordinates, which makes the problem the camera relocalization. And if the reference system is one of the objects, you could consider it as object pose estimation problem. In our case, we want to predict the pose of every object present in your image with just RGB image without depth information. We all know that in our daily use, the mobile phone or the camera at the end of a robot's arm, this is quite a lot of scenarios that we don't have the depth camera. So, and what if under the assumption that we have the geometry model of the objects. In our case, it's a 3D point cloud of that camera, of the objects we have. So basically, the problem we're trying to solve is find the geometry relationship between objects and the camera. That's it. Since it's quite a fundamental problem in computer vision, there are a lot of fantastic work that's working on this one, and we classify them into two categories. The first one is we call it classic geometry method. This method basically based on the 2D and 3D correspondence matching. They have a very elegant framework for this problem. They divided the whole process into three stages. The first one, finding correspondence between 2D and 3D images. The second one, they generate a whole of hypotheses. And then the last one, they try to refine it with optimization method like that. Still, I believe this method still gets the best result for a lot of tasks even during the current time with a lot of methods that based on neural network. I think the main reason is they have a really good framework to try to solve the geometry problem. But one case that this method could fail because when they have some textureless scene or textureless objects, it's really hard to find a correspondence based on just on color information. So the second method in this category will try to match the boundary of the object without any texture information. Let's say it can divide the object from the background with the statistical information of the object or the background. And then they also be called some template matching method, which they find the best shape of the 2D shape in the image and try to find the best matching boundaries of the object with certain pose. But this one also has ignores interior texture cues, which is quite important for objects with cues or with textures. So with the huge development of this recent years with neural network, there's a bunch of CNN-based method as well. The idea of this method is also followed by the classical geometry. They have a CNN to predict a path or initialization of the pose, and then try to use another process, post process we call it, to refine the pose. So in our wish list, we want a method that could be accurate as good as this method. We want it be simply enough without any post-processing of the prediction from the neural network. We want it fast, which is quite similar to the simply wish list. And at last, and one thing that most of method didn't consider is if there are multiple objects present in the scene and they are in the same class, like there are multiple chairs in the scene right now. There are two microphones here right now. How can we simultaneously predict the pose of this object? Just one single inference. A quite straightforward solution of the problem I proposed is try to find the 2D information, 2D cues in the image. First, we can detect the bounding box of this object in the image, and then we predict the mask of all these objects, and at the last we try to using the appearance of this mask or the bounding box to regress to predict the pose of these objects. As we all know, the first two steps is quite common to the research in this field, and we all know there's a method called mask RCN to solve these two problems together in a simultaneous way. So could we do it in rather than doing it in doing the post estimation as a post processing? Can we do it in this parallel with these two, with the first two steps? Yes, that's the goal we want to achieve. So in this class, I will introduce our proposed solution. We call it the architecture. We call it LeNet. Back then, I think this work has been done about half a year ago. Back then, there's no official release of mask RCN. The first author, Tuan, in our group, implemented this code himself based on a cafe. So that enables us to add another head along with these first two heads, which is doing the box localization and the classification and the segmentation task all simultaneously. The difference we're making is this head. We call it the post-animation branch. It took the region of interest, a feature from the region of interest, and directly with several linear fully connected layer, and then we predict the pose of the objects in the scene and simultaneously segment or bounding boxes of these objects. And here you can see, since the problem we are addressing here is to find the 6th degree of freedom pose for each object. But here you can see we only predict 4 parameters for the pose representation. Why is that? To answer, you can never recover a 6th of pose just from just the 4 parameters. Is that right? So to answer that question, let's first find out what's these 4 elements. Okay. The target for the post estimation branch is a 4D vector. The first 3 will be Lie algebra for representation. There are also some other representation for rotation, like the Euler angle, rotation matrix, and quaternion. We all know that the Euler angle wraps around 2 pi, and multiple value represents the same pose. And the rotation matrix or quaternion have the strong constraints, such as it has to be, for the matrix has to be orthogonal, and for the quaternion has to be a unit vector. So we choose Lie algebra as a representation for our rotation. It is a domain of rotation matrix, and the Lie algebra it's a tangent space at the entity of the Lie group, which is big SO3. Each element in the Lie algebra can be represented by a 3 scalar number without any constraints. This is makes the training progress easier. So what's the last one? The last element, as we all know that if you want to represent a translation of the vector, you have to use 3 elements, but here we use only 1. Why is that? Because you know what the property of the neural network is, we all know that in a detection or the segmentation task, the neural network tries to ignore the image position, which is, we call it a spatial invariant feature. But the object, if you have 2 objects in the scene and you give the post branch with the same representation but with different supervision, the neural net could be very confused about how to learn these poses. So we just, but the point we want to make here is the object size and the scale of the texture gives us a very strong cue about z, so we just ignore the x and the y. We recover the x, y, x, and y of the translation with the camera model, since we have the position of the bounding box. Here, in order to train our neural network in an end-to-end way, we design a multitask loss. This loss consists of the classification loss, the segmentation loss, and the last one is the bounding box loss, and last one will be our post loss. So we train this neural network on data set. We call the data set lean mode, and there are 15 object sequences, and we randomly choose 13% of the whole data set as our training images. Here is some quantitative result of the metric we're using here is try to measure the average distance between the point cloud that transferred by ground truth poses and the prediction poses from neural network. If the average distance is smaller than 10% of the object diameter, we consider this prediction is correct. So without any post-up refinement, we achieved about 65.2% of the correctness, and we can compare it to other state-of-the-art method without any post-up processing, where we could achieve the best result. We're still competitive with others if they have the post-up refinement. Here is a small short video about the qualitative result. We are trying to show if we have the right prediction of the pose, we can add another component to the object we want to add. Here we put an Iron Man mask on the ape, and the next one we put a detective hat on a dog, which is kind of good. I have to say. So. And in the next dataset, which we apply this model on the multi-object class task, you see there's 3 different cup or mailbox here. We simultaneously second from the images and predicting the pose as well. I'm going to wrap up this presentation with some failure cases. As we can see from this picture, our method is not very robust to rotational symmetrical objects, such as this coffee box, but we can definitely predict where are these boxes in images if we have the bounding box information. So in conclusion, our contribution consists of 4 parts. Well, the first one, we propose an end-to-end framework and joint 60 pose estimation with classification, detection, and the other 2D tasks. And we directly regress the 60 object pose from single image without any post-processing. And at last, we achieve 10 frames per second, which is, I think, it's enough for real-world application. Thank you very much for your attention. And if you want to ask any questions.
Thank you. We have time for one question. Okay, I have one question.
Thank you.
So you appear to, the pipeline for the pose seemed to be independent of the pipeline for the other 2 pipelines.
Yes.
Is that the case?
Yes.
Is there any, could you use information?
Yeah, that could be a very good idea to try if we have the bounding box of the. Yeah, I don't have a direct answer to it right now, but I think that's worth to try in the future. I think, yeah, if you have the 2D bounding box, you know the X, Y, and the in the translation could be helpful to learn the pose. Or, yeah, so. Yeah.
Thank you very much.
Thank you. Thank you for it.
So today I will present our work on scene coordinate and correspondence learning for image-based localization, which was done in collaboration of Technical University of Munich and Siemens Corporate Technology. So as you all know, SLAM is a currently widely researched topic in computer vision as well as in robotics and navigation to guide a robot and simultaneously build a map of the environment. But due to rapid camera motion occlusions or textureless surfaces, tracking of the camera can sometimes fail. But what actually happens in this case? Worst case scenario, it will require reinitialization of the whole system to rebuild our map. So this is the application we were focusing on in our work. How can we actually relocalize from a single RGB input image? So cameras are nowadays usually available in most devices, so it would be very valuable if we could actually use only the RGB, or maybe also if you have a depth camera, the available image, to robustly predict our camera pose. This would also remove the need for any additional sensor information required to do robust localization. Image-based localization has been widely researched in the last few years. The most related to our method can be divided into 2 groups, scene coordinate regression and direct pose regression. Initially, regression forests were used to predict scene coordinates given RGB and depth features extracted at image pixel locations. Then, since usually there were erroneous predictions, a robust pose was computed by a preemptive ransack optimization. So multiple pose hypotheses were sampled and then scored based on the inlier count and refined using those inliers. But since this ransack optimization can be quite computationally expensive, direct pose regression methods emerged, which were actually able to compute a pose using only one forward pass of the network. So here, for example, you can see results from PostNet, which was the first one to introduce direct post-regression methods. But since this very efficient method came with a drop of accuracy, there have been various extensions and optimizations of this method. For example, including LSTMs, or also in the form of a Bayesian network to introduce or to deal with uncertainties in the post-prediction. Simultaneously, since there was always a kind of trade-off between post-accuracy and computational time, switching from regression forests to deep learning methods, a differentiable version of RANSAC was introduced, which connected two neural networks, one for scene coordinate regression and one for post-hypothesis scoring, into an end-to-end trainable pipeline. Also, most recently, which should be mentioned, there was another direct post-regression method, VLOGNet, which introduced or which proposed to use relative post-information between image pairs and included that into the network, and was actually one of the first methods to achieve comparable results in post-accuracy compared to scene coordinate regression approaches. So our method is actually most related to scene coordinate regression methods. We use the existing pipeline. But also what most of these works have in common is they try to deal with uncertainties in their predictions, either by sampling multiple post hypotheses or by directly using a Bayesian network and dealing with uncertainties in the post directly. So this is also one of the major focuses of our work, how we can deal with uncertainties. But in our case, we go back to establishing correspondences. So here, for example, you can see resulting pixel to 3D scene coordinates from which then the post can directly be computed, solving the perspective endpoint problem. But as I mentioned in earlier methods, these outliers were usually handled using a rather computationally expensive RANSAC optimization. So usually RANSAC can compute a good post estimate even in the presence of outliers. But then there's always a trade-off kind of between the computational time if you have a large amount of outliers in your data and the accuracy it can give. So this is where our work sets in. So we would actually want to optimize this, this process and learn how to how to predict confidences for our correspondences, how well they actually match. So for inliers or very good correspondences, we would want to achieve high probability, so we can discard outliers right away. But how do we actually do this? We propose a three-step framework, which starts with scene coordinate regression. So initially, given an RGB input image, we densely regress a pixel-wise scene coordinate map for the RGB image. And in this case, we used UNet to train our network, which follows an encoder and decoder network architecture with skip connections. And we evaluated different loss functions, in particular L1 loss and Turkey spy weight loss. We also applied an additional regularization in the form of a depth-based coordinate smoothing over a local neighborhood of an image pixel. So if depth values in the surrounding neighborhood of the image pixel were really close, we assumed that the scene coordinates should also be kind of smooth, and we apply a weighting in that case. If there are edges, for example, or huge differences in depth, we try to give it lower weight to neglect these points. So now to our main contribution, the confidence predictions. Once we have regressed our scene coordinates, we apply a second network, and we randomly choose correspondences predicted by our first network as an input to a point-net network architecture. Then for each of these correspondences, we will obtain a probability of how well this correspondence actually matches. So now we could actually also easily approach this as a classification problem. So for example, in previous methods, usually how this RANSAC optimization was done is by setting a threshold, for example, 10 centimeters in distance between our 3D scene points. So we could actually also identify this as a classification problem, a binary one. So you just classify it as an inlier or an outlier, and then afterwards remove the outliers. But this threshold we choose would actually strongly depend on our initial scene coordinate regression and also of the scene we are currently relocalizing in. Since if it's a very difficult scene, we should always choose this threshold accordingly. So instead, what we propose is to address this as a regression problem. So in this case, for each of our correspondences, we can actually map the probability to the distance between the ground truth and our predicted scene coordinate. And to evaluate our method also to the state of the art, we actually match this so that we can easily match between our probabilities and, for example, this inlier threshold chosen of 10 centimeters. So now to our final step, the actual pose estimation. Here we follow previous methods. Once we have obtained our request scene coordinates and our probabilities, we can actually use the resulting correspondences and compute the pose by solving the prospective endpoint problem. In our case, we used EPNP. And we follow previous methods and do additional pose refinement to optimize our accuracy. So in this case, we sample multiple pose hypotheses, and we score them according to the confidences of the sample points. So our confidence prediction can also help in pose refinement afterwards. And then afterwards, once we have ranked our pose hypothesis, we optimize the best one by sampling additional confident points. We evaluated our method on the publicly available 7 scenes dataset from Microsoft, which consists of 7 scenes, ground truth camera trajectories, RGB, as well as depth images. To evaluate our confidence prediction, here you can see some visual results where we show the input image to our network, the resulting point error map, distances between the ground truth and our predicted scene coordinates, and the resulting confidence map, which was regressed during the second step of our framework. And you can see here that there's a high correlation between the point error map and the confidence prediction. So in cases where we have really well-regressed scene coordinates, our confidence prediction gives very high values. So we have actually found a very good match. Then to further evaluate this, we create a baseline and sample, for example, 500 randomly chosen points, from which we then compute the pose estimate, and we compare to our proposed confidence-based sampling, where we only use the most confident points, hoping that in this case we can actually immediately discard erroneous predictions. And we can see that if we evaluate different models and our confidence prediction, that there is a significant increase also in the percentage of inliers of our points, which are then used for pose prediction. Also, if we switch from the correspondences to actual pose accuracy, we can see that the rotation and translational error significantly improves on all of the scenes in the dataset. So here you can actually see that we have a very good improvement of our initial pose hypothesis and can discard erroneous predictions immediately. Also, to show you some visual results, we reproject the 3D scene using our predicted pose estimate, and we plot the camera trajectories. Here it's also again visible that we can remove outliers very efficiently, which results in improvements in our pose estimations. To optimize our pose accuracy further, we do pose refinements. In this case, we sample additional very confident points, and we refine our pose on those points. Here you can also see some visual results. And yeah, as I mentioned, this results in further improving the method's accuracy if needed. To compare to the current state of the art and on scene coordinate regression as well as pose regression, we achieve comparable results, but for example on the challenging stair scene, which shows a lot of repetitive structures, you can see, for example, that our method predicts more robust pose estimates than, for example, the current state-of-the-art differentiable RANSAC on scene coordinate regression. Although it should also be mentioned that VLOGNet and also the differentiable version of RANSAC already published extensions of their method. So to summarize, we have proposed a very efficient method to regress pixel-wise scene coordinates given an RGB input image, but most importantly, we add a confidence prediction for our obtained correspondences, which we can use to discard erroneous samples right away. Also, this is a very robust and general solution, which can then afterwards also aid in pose refinement using the obtained confidence predictions. It should also be mentioned that since we only sample very confident points, we can actually also keep the number of points to a minimum and the computational time of our method to a minimum. Then thank you for your attention. I will be happy to answer your questions. So, yeah, actually, for example, instead of sampling 500 randomly chosen points, we only use the 10% most confident, so which results in an amount of 50 correspondences used, which is the first step to increase the computational time, and also we compare to the state of the art, for example, the differentiable ransack, and we were also able to significantly improve the computational time there. I think we only refined our method with 8 iterations. So we only sample very confident points, and since they are already quite good, post-refinement can easily be done.
Thank you very much.
Good morning, ladies and gentlemen. Thanks for being here. I hope you have a great conference. Today, I'll present our work on non-smooth M estimator for maximum consensus estimation. So firstly, let's go briefly into the introduction. Our work focuses on the robust geometric estimation, which is a fundamental problem for many 3D vision applications. For example, fundamental matrix estimation, homomorphic estimation, especially structure for motion and SLAM, to name a few. To define robustness, there are a lot of criteria. However, maximum consensus is considered one of the most popular robust criteria. The goal of maximum consensus is to find the estimate that maximizes the number of inlayers. Here, we show an example of homomorphic fitting problem, where the inlayers that we need to find is a set of correct matches, which is plotted in green. In practice, this set may be contaminated by the set of outliers, which are plotted in red. Maximum consensus can be expressed in terms of an optimization problem 1, as shown in this slide. Here, theta is the parameter that you need to estimate, and I is the consensus set, and we would like to maximize the cardinality of I. Here, the f functions is the quasi-convex residual functions, which can be defined differently for different applications, and epsilon is the inlayer threshold. So to solve maximum consensus, randomized methods such as ransack and its variant are arguably the dominant method in the field. The mechanism behind these methods is that they randomly sample minimal subset, and for each random sample subset, a hypothesis is estimated, and then the number of inlayers is measured. And after a fixed number of iterations, or after a large enough number of iterations, the hypothesis with the largest number of inlayers is returned as the result. These methods work well in practice. However, one of the weaknesses of these methods is that they are non-deterministic, which means different executions may result in different solutions, and there is no guarantee on optimality of these solutions. Therefore, our goal is to develop a deterministic algorithm which satisfies 3 criteria. Firstly, it must solve the maximum consensus problem in a deterministic way. Secondly, it must improve upon the randomized solutions. And thirdly, the conversion of the algorithm must be guaranteed. Our work strongly resembles the conventional M estimators, which again is a well-known technique in robust estimation. In order to encourage the inlayers and discourage the outliers, M estimator introduces the robust loss functions, which can be chosen from a variety of functions, for example, Hilbert loss function, Cauchy, or Tukey's. While when expressed in terms of the optimization tool shown in this slide, iteratively reweighted least square is a well-known technique to solve NFM estimator. At each iteration of IRLS, a weighted least square problem is solved, and then after that, the data points are then reweighted based on the current residual. With this scheme, the conversion of M estimator is guaranteed, given that you chose the right loss function. Arguably, the use of M estimator with robust smooth loss function can also be applied to our maximum consensus problem. However, there remains some problem. Firstly, the use of smooth loss functions do not well approximate the maximum consensus loss function. To illustrate that, here we plot the loss function for the maximum consensus in blue, and the red functions are the function with the smooth loss function. As can be seen in this plot, with one blue function, we can have multiple red functions to approximate that, and the choice of the correct loss function to approximate the blue functions is ambiguous. Moreover, by using the M estimator with smooth loss function, some implicit assumptions about the noise distribution of inliers must be assumed. Unfortunately, because our maximum consensus contains a non-smooth loss function, the traditional IRLS cannot be applied directly to our case. Therefore, we introduce AMES, or ADMM-based M estimator, to tackle this problem. ADMM stands for Alternating Direction Method of Multipliers. I think most of you already know, and it's a popular optimization technique that has attracted a lot of attention recently in computer vision. So, our algorithm has three main characteristics. Firstly, it solves the M estimator with non-smooth loss function, and to the best of our knowledge, we are the first to tackle this problem. Secondly, AMES results in a better solution quality, and finally, the conversion of our algorithm is guaranteed. Now, let's deep dive into the mathematical formulation of our problem. First, let's write the original maximum consensus problem. Now, in order to put maximum consensus into the context of M estimator, we can write the original problem, which is 4 in this slide, as the optimization problem 5. Here, the big 5 functions is the square functions as plotted. The intuition behind this formulation is that by minimizing the objective function of 5, we are minimizing the number of outliers. Therefore, we maximize the number of inliers. Now, in order to apply ADMM into our problem, we need to introduce n auxiliary variables, theta 1 to theta n, which correspond to n observations that we have. Now, we already turned our original problem 7 into a new constraint optimization problem 8, where the constraint we have is the coupling constraint to make sure that the auxiliary variables that we introduce must converge to the same original variable theta that we have. And note here that 7 and 8 are totally equivalent. Furthermore, to support the conversion of our algorithm, we introduce another regularization term, which can be written as 11 and 12. Note here that even though we call it regularization, 11 and 12 and the original problem are still equivalent, means there is no relaxation at this step. As we already have the new formulation, we are now ready to write the augmented Lagrangian of the problems at 15 and 16. Note here that the lambda are the scale Lagrangian multipliers with respect to the auxiliary variables that we introduce, and theta is the penalty parameters. Since we already have the augmented Lagrangian, now we are ready to introduce the ADMM update. Firstly, we will update the auxiliary variable that we introduced, theta I, by solving the optimization problem 17 as written on the slide. One interesting point in this optimization problem is that this is a quadratic program with one quadratic constraint. That means it can be solved up to global optimality just using bisection. Another interesting point in this one is that due to the fact that all the auxiliary variables are all independent, these variables can be updated in parallels, means this step can be implemented using multi-threading. After all the auxiliary variables are updated, we are now ready to update the original variables, which can be done by solving the optimization problem 18 written in this slide. Due to the fact that this one is just a convex least square problem, this can be updated in closed form solution using KKT condition, which is written in 19. Finally, we can update the Lagrangian multipliers lambda I, which can be updated at 20. This can be thought of as accumulation of the deviation of the auxiliary variable from the original variable. One contribution of our works is that we prove that the iteration that we introduced previously converges to a stationary point of the Lagrangian, given that the rho is chosen to be sufficiently large, means our algorithm will not diverge. Here, we show a representative example result of our algorithm. In the top plot, we plot the consensus side with respect to different rate of outliers. While all the methods are initialized with the same starting point, it can be shown that our algorithm can upgrade this initial solution to a very good consensus size compared to other methods. The thing that we want to note here is that due to using the correct loss function by applying our methods, the cost function of maximum consensus can be upgraded to a very high compared to its approximation method, like by using Hilbert or Cauchy loss function. Also, due to the fact that our algorithm can be parallelized, we achieved faster solution compared to other competitors. So, in conclusion, traditional M estimator is a commonly used technique for robust estimation. However, when it comes to maximum consensus, the smooth loss function does not well approximate the original function of maximum consensus. Therefore, we introduce a mesh which solves the maximum consensus problem in the context of M estimator with non-smooth loss function. And our algorithm converges after a finite number of steps, and this is guaranteed. Finally, we empirically show that our method provides better solution quality for many robust fitting problems in computer vision. For future work, we will investigate the use of AMS for large-scale reconstruction pipeline. And secondly, we can think of how to integrate AMS into deep networks that requires the use of robust geometric estimation. With that, I would like to conclude my talk, and thank you for your attention, and I'm ready to take questions. This is still a local optimization method because maximum consensus and NP-hard, and we try to turn it into optimization, but it's still a local method. It's not a global method. Actually, if we go back to our formulation, well, actually, like this can be considered as a optimization problem. Of course, it's a non-convex problem. Even though it's a smooth optimization problem, it's still non-convex. So theoretically, we can use any non-convex solver to solve this problem.
Thank you very much.
Thank you.
Good morning, everyone. This is Taeyong Song from Digital Image Media Lab, Yonsei University, South Korea. Today, I will be talking about deep network for simultaneous stereo matching and dehazing. This research is done with Youngjun Kim, Changjae Oh, and our advising Professor Kwang-Hoon Son. The presentation is organized as follows. First, brief review of stereo matching and dehazing with their challenges will be given. And the main motivation for the research will be presented. Then I will introduce our proposed deep network for simultaneous stereo matching and dehazing. Experimental results will be given, followed by conclusion. Stereo matching is a computer vision task to estimate disparity given left and right or stereo images by horizontal correspondence searching. With camera calibration parameters, disparity is inversely proportional to the scene depth. Recently, stereo matching methods have achieved fast and accurate results with CNN. So far, those methods have only considered stereo images captured in clear weather. However, in real outdoor scenarios, we are often faced with haze. Haze is an atmospheric phenomenon that small particles in the air scatter light and attenuate the appearance of images. In hazy situations, stereo matching performance is degraded due to low contrast and faded color. The figure below shows how a stereo matching network trained with clear images perform for clear and hazy stereo pairs. Haze results in degradation of images' visual quality as well as the performance of higher-level computer vision tasks. Therefore, image dehazing has also been a popular research area for computer vision. Hazy image is modeled as following equation. It can be interpreted as weighted summation of clear image and air light with the transmission for the weight. Assuming homogeneous atmosphere, transmission can be expressed as an exponentially decaying function of depth. Most of dehazing algorithms follow the pipeline to estimate transmission and air light to recover the clear image by inverse calculation of the hazy image model. Here, we can take a moment and notice that both stereo matching and dehazing tests estimate depth-relevant features, disparity, and transmission. To continue, transmission estimation usually relies on the pixel colors as haze results in saturated color. And there frequently happens a phenomenon called air light albedo ambiguity. It is a phenomenon that haze density is overestimated for the objects with saturated color disregarding the actual haze level. This ambiguity is more common and has more impact for close objects and results in artifacts in the hazed result. Now we introduce our strong motivation for the proposed method. We observe that stereo matching and dehazing obtain their depth cues in a complementary way, and therefore they can help each other. To be specific, for close objects, dehazing gets more impact from the air light albedo ambiguity. On the other hand, close objects have more preserved and distinctive image features with light haze. Reliable stereo matching for close objects can help the dehazing task to estimate the transmission more accurately. For distant objects, stereo matching performance will be degraded because degraded image features cause confusion in the matching cost computation. However, dehazing task can acquire the depth ordering from the gray level of the pixels. Depth cue from the dehazing can help the stereo matching for hazy regions. From this motivation, we designed the proposed deep network for simultaneous stereo matching and dehazing. Our overall architecture is composed of two networks, stereo matching and dehazing. And the dehazing network is further divided into transmission network and air light network. First, I'll describe the stereo matching network. Our stereo matching network is a variation of DisNetC, but with an additional upsampling. It takes hazy left and right images as input and estimates the disparity map aligned to the left image. For more details, it has two parallel convolutional layers with shared parameters to extract features from left and right images. Then the correlation layer calculates the similarity volume from the extracted features. The output disparity map is regressed from the similarity volume through the encoder-decoder architecture. Next, I'll introduce the dehazing network. First, the transmission network takes the hazy left image as input and estimates the transmission map. Considering its more critical impact on dehazing compared to the airlight, it is designed as an encoder-decoder network similar to the stereo matching network. The airlight network has a more compact architecture. It takes left hazy image and estimates the airlight through 5 convolutional layers. Our overall architecture has feature sharing by concatenation at the end of each encoder of stereo matching and transmission networks. By feature sharing, depth queues from 2 tasks are incorporated into each other. We chose the location of feature fusion in a way that the 2 networks can share the most informative features. Now, loss functions to train those networks will be introduced. First, I'll introduce our new loss for dehazing. We name it as hazy image model loss. Using the hazy image model equation, we first reconstruct hazy image with ground truth clear image and estimation of transmission and airlight. Then the loss is defined as the L1 distance between reconstructed hazy image and input hazy image. With this model loss, correlation between transmission and airlight is established, although they are separated network architecture. To optimize the whole network, we use L1 losses for disparity, transmission, and airlight. For transmission and airlight, we add hazy image model loss for interaction between those 2 networks. And for the disparity, we adopt multi-scale loss and weight scheduling. Total loss is the summation of all 3 losses and optimized with single solver. Let's see our experimental results. Our main experiments are conducted on the SynFlow dataset. And first, for the stereo matching, we compare our method with 2 naive solutions for stereo matching in the haze. Those 2 naive solutions are, first, applying dehazing and stereo matching sequentially, and fine-tuning the stereo matching network with hazy images. We can see that our joint network obtains the most accurate disparity. And for dehazing, we can see that a separate dehazing network suffers from the airlight albedo ambiguity. Lower transmission means more dense haze, and we can see that although the white box is close enough to suffer less from haze, the separate transmission network estimated the transmission to be very low, which means a dense haze. However, with the depth cube provided by stereo matching network, the joint network estimates transmission and dehazed results more accurately. Quantitative results for stereo matching is given. On the table, we specified the type of images the networks are trained and tested with. The first and the second row show how a stereo matching network trained with clear image performs on clear and hazy situations. Those measures are used as references. Results of 2 naive solutions and our proposed methods are compared. And we can see that our proposed network produces the best results. We also compare our method with previous handcrafted stereo method that takes the haze into account. We can see that our CNN-based method outperforms the previous method. And for dehazing, we observed the impact of hazy image model loss and the joint learning with stereo. We can see that the hazy image model loss results in slight improvements, and joint learning resulting in larger improvements. Finally, we compare our dehazing performance with previous dehazing methods. Our separate dehazing network and joint network both show superior results. Now we conclude the presentation. First, we propose a CNN framework for simultaneous stereo matching and dehazing based on a strong motivation of complementary nature of stereo matching and dehazing in terms of depth cues. And we proposed a new hazy model loss for improved dehazing performance. However, our method also has limitations. First of all, our method is fully supervised. Especially, it requires dense and accurate ground truth disparity for both left and right images to simulate the haze on both stereo images. Therefore, although we present visual results for real data as an additional experiment, our main experiments were limited to a synthetic data set. So our future work will be establishment of well-organized approach for the generalization to the real data. Thank you for your attention.
Yeah, I'm just about to say the question is coming from the behind curtain on your side. So thank you very much for your talk. So my question is, when introducing the architecture, you mentioned that you do the feature fusion in a way that most informative information can be exchanged. So you formulate it so that the middle feature vector is concatenated. But my question is, since you use a UNet-like structure, a lot of information is getting through the bypass and the skip connections, and it's in order to preserve more information than just going through the middle layer. So I wonder if you have any comment on that, and I wonder what's your opinion of what is the role of the middle bottleneck feature layer in like a UNet setting? Thank you.
It is known that earlier stage of CNN network extracts more basic features such as edges, and as the layer continues, the more informative features are extracted. Therefore, I wanted the networks to share the most informative features. And I also considered the loss of spatial information during the pooling and convolution operations. And after this paper work, I have continuously done with many different architectures for this simultaneous network. So, yeah, that would be my comment for your question, if it will be enough for your question.
Thank you very much. This is the final talk of the morning session.
So sorry about the interruption. Hello everyone, my name is Yi Zhang. Today I'm going to introduce this work, Sample Ahead, online classifier sample communication for learning from synthesized data. This work is jointly done with Qi Weitao Qiu, Ling Xixie, and Anna Yu. There is a growing popularity to use synthetic data in computer vision tasks, especially tasks that need fine annotation, such as stereo, semantic segmentation, human pose estimation, and optical flow. Even with domain shift, computer vision algorithms still benefit from synthetic data by virtue of adding a huge amount of training images with long choose. Take render for CNN as an example. The combination of camera pose and object models allow them to add 2.4 million images to original Pascal 3D Plus training sets. But 2.4 million is just a tip of the iceberg from virtual worlds, or I would say a ping pong ball at the top of the iceberg, because for an iceberg, the underwater part is around 90%, while we can generate much more. There are numerous parameters that take a virtual scene into a static image. For example, camera pose. We have azimuth, elevation, tilt, and distance, and the same for lighting, texture, material, and scene layout. So suppose we simply sample 1,000 possibilities of each parameter listed. Would you like to guess how many images we can generate? So, yeah, that's 10 to the 39th. But remember, they are just samples from the virtual worlds. So, what we are facing here is an infinite image space. Thus, we identify a new problem, which is from the infinite data space, how to sample finite amount of training data that best facilitates training. Previously, people have built repositories of 3D models like ShapeNet, and there are works utilizing game engines to obtain synthetic data from complex and realistic scenes from films and video games. And in active vision, the work from Yararaman manipulates viewing parameters at test time to maximize the confidence in making a prediction, and others use navigation in an interactive visual question answering setting. And there are plenty of literature that adjusts sampling probability given a fixed finite training data, such as online hard sample mining. So while our work aims to effectively sample synthesized data from an infinitely large parameter space. So how do we do it? The idea is very simple, which is to increase the probability of hard examples being trained. In traditional way of using synthetic data for model training, images are generated from virtual worlds beforehand, and at each epoch, the model travels through the same image set, while we propose to change the rendering parameters according to the prediction at each epoch. So our innovation is that we add a sample ahead module to the training process to predict training images for the next epoch. So how does sample ahead module work? First, we train the model for one epoch with the initial rendering parameter and the rendered image set. We then set aside a probe set, which is, can be considered as a validation set divided into several buckets according to different rendering parameter ranges. Then we forward the probe set through the frozen model at the current epoch. By evaluation, we could approximate the difficulty of each bucket combined with the initial sampling probability of the rendering parameter. We can update the sampling probability according to this formula so that the buckets of rendering parameters with
less difficulty are less sampled. Then the exact rendering parameters are uniformly sampled within each bucket. Thus, we obtain a new set of rendering parameters. We then generate a new image set according to new parameters and train the model on this image set, and the process is repeated. So we demonstrate the effectiveness of our methods on two tasks. First task is digit classification. We use data augmentation on MNIST as a method to synthesize images. The rendering parameters are digit class transformation parameters like shift, shearing, rotation, and scaling. The probe set is 16,000 images augmented from 50,000 training images. And the model we use here is LeNet for the baseline. It's just a uniformly augmenting training images with parameters in each bucket, while our method updates the distribution of all buckets. We run the experiment for 10 times and we achieve lower error than the baseline. And when the number of iterations are smaller, which means using fewer training data, our improvement over the baseline is more significant. Another task we perform is object post-estimation, where we render images from ShapeNet 3D models. The render process is the same as render for CNN by SU 2017, and the parameters are object classes, azimuth, elevation, and to narrow the search space, we set other parameters as render. And the probe set is a split of real images in the training set of Pascal 3D Plus. We then compare our results to the baseline method from SU, which is their improved result in their released code. They generated 2.4 million images from the distribution of Pascal 3D Plus training data. For the joint task of detection and azimuth estimation, we achieve better accuracy in every fine level of azimuth division. And what is interesting here is that as the division of azimuth increases from 4 bin to 24 bins, which means the task becomes more difficult. Our improvement over the baseline is more significant. This aligns with our methodology because we are mining hard examples. To evaluate how the post-estimation part works, we use VUC easy dataset with ground truth bounding boxes. Here we achieve the same mean accuracy as the baseline, but lower error. We did some ablation study for our method. So for our method, we mainly benefit from two abilities. First is update the sampling distribution according to difficulty of training examples. And second is generating new data based on updated distribution. Switching off the first turn it back to the baseline with more data sampled, while switching off the second means we only allow our approach to sample from the original 2.4 million synthetic images. In both cases, accuracy drops. So this shows that both generating and sampling strategies are useful yet complementary to our approach. We also investigate on why our algorithm works. So in the baseline method, they sample training data from a fixed distribution, while finally leads to an imbalance of accuracy distribution with respect to the rendering parameters. In our method, we sample more data from regions that have lower accuracy so that the accuracy of these regions increases without compromising other regions too much. So to summarize, we identify a new problem of how to effectively sample synthesized data from an infinitely large parameter space and design a novel sample ahead module that can be attached to the training process to enable communication between classifier and sampler. This method is simple yet effective, as shown on the mentioned two tasks. Though we only show two tasks, both the problem and our method are complementary to many computer vision tasks and learning models, as long as we can freely render images from the virtual worlds. Thank you. If you have any questions, I would be happy to take them.
Yeah, like how do you make sure that your network will not overfit to the hard examples in the following epochs?
So I think I can come back to the updating formula. So here we control the sample rate from the difficult examples and the initial examples by the alpha. So here alpha we set to be 0.9, which means we don't want to change the distribution too quickly to prevent like overfitting.
So like in epoch 2, for example, will you use P of 0 or you would use P of 1 in that case?
P of 1.
Ah, okay.
Yeah.
I see.
Okay. Thank you very much.
Thank you.